Okay, please.
Okay, hello everyone. We're Group 1, and this is Catherine, Stone, Taylor, and Jer, and we were conducting our scientific investigation project on fruit waxes. So, we know that from our background research that fruit waxes contain chemical residues from the processing and initially from the plant. And from other studies, we know that this can increase the half-life of certain pesticides and insecticides. And on one hand, this can help preserve them for a longer period of time, but on the other hand, as a consumer, you probably wouldn't want these potentially harmful chemicals to be ingested when you're eating an apple. And what the fruit waxes actually do is it forms a layer around the apple, which helps the apple retain its water, and this can help it have a good appearance by shielding it from physical damage. It can also help preserve it by slowing down mold growth, and it also heavily slows down oxidation, which would cause browning of the apple. And the problem with these waxes are that since they're regulated as food additives, they actually aren't inspected after they're initially approved by the CFIA, unless there's a heavy amount of evidence showing that a component might not be safe in them, as in the case with morpholine, which was actually retested in 2005 by the CFIA, and they did a very extensive research on that. But that's obviously not possible unless there is actually independent studies that actually can show that there are compounds in these waxes that are unsafe. So our goal is to find a simple and accurate method of determining the compounds that are within these waxes in order to investigate them, and so that we can check the safety of them.
So, in order to do our experiment, we choose two types of apples. One is the conventional apple, and the other one is the organic apples. We purchased one conventional apple, which brand is USA Fuji, and we purchased the organic apple, which is Gala BC organic apple from Grocery Tracker Market. And then we are going to use two instruments to analyze the fruit wax coating. One is GCMS. As you know, GCMS is gas chromatography mass spectrometry, and which can identify possible components in the wax coating. And it also can help us to find out that the more volatile components move faster and be detected first. And so we will get a library that shows different components have different retention time. And in our experiment, in our instruments, the helium will be the carrier gas, and we set the temperature as 250 degrees Celsius, the pressure at 7.7 psi, and the total flow was 23.1 milliliter per minute. And for FTIR, as you know, it's Fourier transform infrared spectroscopy, which can provide functional group percent transmission, and it can also be the support information that help us to find out the possible components from GCMS library. So in our methods, we first wash with one conventional apple, and then we use paper towel to wipe the water on the skin of the on the apple. We do that because we want to make a comparison between washed apple and unwashed apple, because most of the people eat apples after washing them with water. And then, although I know that the skin of the apple is hydrophobic because of the wax, so we still want to make a comparison between the washed apple and unwashed apple. So after we wiped out the water on the wax coating, we directly put it onto the FTIR scan, and we we scan 3 different sizes on the apple surface, and we get 3 different spectrum from that FTIR. And next, we use 2 conventional apple, but without any wash or any treatment. We directly use the stable to scrape the skin. And then we put all of the 2 conventional apple skin wax into one 10 milliliter beaker, and we got this creamish white powder. And we put some of the powder into the liquefier and then dissolve in chloroform, which is a good solvent to dissolve the wax coating. And then we put into GCMS to do analyze. For the organic apple, we do the same thing. Without any wash or any treatment, we directly use the stable to scrape the skin and then put all of the wax coating powder into one 10 milliliter beaker, and we got this grayish white powder. And we also do the FTIR and GCMS. For the FTIR, we are going to do 3 rounds for each of the unwashed apples. And also, we also find out that we scrape more of the skin wax coating from the conventional apple, and we suggest that because conventional apple has thicker skin than organic apples. And Saren and Stone is going to perform our results from our methods.
Yeah, so as Catherine mentioned, we did 2 FTIRs on the organic apple wax and the conventional apple wax separately. So these are the chromatograms of those 2 apples. As we can see here, the chromatogram have like major difference. The organic apples have like 2 major peaks and multiple small peaks. But on the other hand, the conventional apples has also only 1 peak, and the like minor peaks are fewer. So let's just take a closer look at the chromatograms. This is the chromatograms from the organic apple, and we can clearly see there are 2 major peaks, and fortunately we are able to identify them by comparing the mass spec data from the library. So we got like this peak, which has a retention time of around 2.8 minutes, is actually the taurine. And the other peak here, which has a retention time of 12-ish minutes, is actually 2-phenylpropyl acetate. So let's take a look at the mass spec we got from the first peak, which is the most major peak here. It's got a massive molecular ion peak, which corresponds to the structure of the taurine. So as we all know, taurine is not a very good agent that could be existing on apple waxes, but either way, we have that on our organic apple waxes, which I think is kind of weird. But taurine can be a form of pesticide, so I guess that's why we have it here. And those are some other structures we found on the organic apples waxes. And there are some common features, such as you got icosane and this kind of a structure, which contain like long chains of alkyl groups. And I think these are the hydrophobic wax part, which maybe contain the water from the apples. And we got like an ester group here, and these are the other major peak, which is 3-phenylpropyl acetate, which got an ester group. And I think that's a natural product on the apple peels, actually. So let's take a closer look at on the other hand, the conventional apples. We have identified the major peak as nonacosane. So these are the mass spec and the structure of the naloxone. As we can see, there are really long alkyl groups here. These are really long, like single chain alkanes. And we got a tiny beta molecular ion peak here, which is 428.5, I think. And like the major peaks are also the fragments here, because this one is really easy to fragment. And those are the other structures we found in the conventional apples. As we can notice, there are 2-methyl-2-pentanol, which is another nasty product, nasty compound we can have on the fruit wax, because it will be really toxic on high concentrations. But those esters are actually fine, and some of them are products from apple waxes. Yeah, so Sarah will tell us about IRs.
Okay, so I guess it's not very clear due to technical difficulties, but this is the overlay of our 3 IR samples, the organic apples, conventional apples, and conventional washed apples, which is new for the IR. Unfortunately, we couldn't put that in GCMS due to any possible residual water, which would have affected the instrument. But we have it here in the IR, and it's kind of hard to see right now, but there are some differences in peak intensities here, and there are some different patterns that are shown, which clearly shows that the compositions in these 3 different samples we have are different. And I apologize again for the not clear display, but these are all closer looks at the IR peaks, and as we can see, there's a peak in conventional apples which is absent in other spectra. Okay, so we found something interesting. Carnauba wax is a component of some of the apple waxes that are out there as commercial waxes, namely Carnauba Gold 2. And we looked at the IR of bleached Carnauba wax, and it's surprisingly similar to what we found. Unfortunately, due to copyright, I can't show the actual IR, but I do have the peaks, and I will show it to you now. So this is our organic IR, and we can see here we have a peak at 2956, 2926, I think 2926, 2849, 1717, 1473, 1171, and 790. All of these peaks are actually present in Carnauba wax. They are really close. So what we concluded from this is that organic spectra is so organic apples have a wax composition that is similar to Carnauba wax. And if you look at our 3 trials, you will see that all of the peaks have very similar wave numbers and very similar transmittance percentages. So from here we see that our measurements are consistent. If you look at the conventional apples, again we see the peaks that are present in the Carnauba wax. So we conclude that this apple may have Carnauba wax as one of the components. However, 2 differences. First of all, in Carnauba wax there's a bit of more noise here with small peaks, and secondly, these 2 peaks that are defined C-carbonyl bond and CO single bond, they're in Carnauba wax, they're a bit more intense, more transmittance. So since Carnauba wax is a mixture of several components, we say it might be a bit different in terms of composition, but it is still a similar wax structure. Again, if you look at our 3 trials, you can see that the peaks are present in all of them, so our measurements are consistent. Finally, our conventional washed apples show that there's still some kind of a wax component here because we can still detect it. However, look at the transmittance, it's 75 as opposed to the 25 we've been having for conventional and organic apples. So this suggests that there are some of it is washed, but we cannot entirely get rid of it just by washing it as a normal consumer. And if you look at the three different measurements we have, the peak intensities change. So 75% transmittance, 55% transmittance, and 70%. This is because this was done with a different method. Instead of scraping it, so having a uniform wax, we did it directly on top of the apple. So different parts of apple have different wax compositions. So washing it doesn't entirely get rid of it, and gets rid of it in different percentages in different parts of the apple. So I'll give it back to Stanford.
Yeah, so actually we did a PCA analysis of all the IR measurement we have, and as we can see, there are 9 dots here. I think those 3 are corresponding to the organic IR measurement, and those 3 prime dots are for the organic, the conventional apples, and those separate 3 dots are from corresponding to the conventional washed apples. As we can see here, those 3 dots are really crammed together because we measured them 3 times in a row. But those 3 are apparently different than from those 3. So we can confidently say that the conventional apple fruit wax are clearly different from the organic fruit wax, which supports our data from IR and GC mass spec. So actually, so those are corresponding to the composition difference. But the 3 separate dots here are, which corresponds to the conventional washed ones, are really kind of separate. But this is because we, as Sarah mentioned, we measured it with a different method. So those are from the scraped polars, as mentioned before. But the 3 separate dots ones are from the are from directly measurement on top of the apple. So they are kind of different, and they gave us information about the washing is actually not getting rid of all the compositions, but but clearly the IRs are different on different spots, and it's also and it doesn't clearly wash out the composition here. So
then, in combining all our data, I made a list of all of the compounds that we identified in both the organic and conventional apple waxes. And so, just so you can see better, I've highlighted the ones that are potentially harmful to human health in red. And that was the toluene in the organic wax, and then the 2-methyl-2-pentanal in the conventional wax. The other ones I've left in green just because they're naturally occurring in plants, such as leaf cuticles or fruit peels. So we didn't see them as being, or something to look out for. But the toluene and 2-methylpentanol can be toxic at high concentrations. So it just depends on how much you consume. And then altogether, just some general conclusions that we were able to draw from our studies. So first of all, as Catherine had already mentioned, there was a much thicker coating on the conventional apples. And so from this, we're just able to know that there could be a higher dose of potentially harmful chemicals on conventional apples just because the wax applied is so much thicker. And as you saw, most of the chemical compounds identified don't pose a risk to human health. So we're not really concerned about those ones, but both organic and conventional apples did contain, or we did find one compound that could be harmful. As also Catherine pointed out during methods, washing apples did not remove the wax just because of the hydrophobic properties of a lot of the chemicals contained in the waxes. We also noted that the apples began to quickly oxidize once the wax was removed, so it is beneficial to apply this wax. And then also our method of testing was very simple and not very time consuming. So we believe that the CFIA could apply our methods to testing their apples before they put them on the market. And then some limitations was that we only looked at one brand for both conventional and organic, and also our apples were only from Canada, specifically BC and Ontario. So we want to expand our studies and look at apples from different countries as well as other brands. And also to draw any conclusions on the safety of consumption of apple waxes, we need to look at concentrations and compare these to limits set by the CFIA. And that's all.
Questions?
Is the fact that you used two different varieties of apples, such as Fuji and I believe the other one was Ambrosia?
The Gala.
Yeah.
Gala, yeah. Does that affect the chromatogram at all, the composition, or how does it affect those?
Well, I think, well, we do believe that different companies may have different compositions of the waxes they apply, so there definitely, the discrepancies in the compounds present could definitely be due to just different companies. But to answer that, I think we would have to go back to the lab and look at a variety of different brands.
And also that two apples is from two different locations and might have different composition of the wax probably.
Thanks.
So the toluene, how do you think it survives? And the toluene's got a vapor pressure. Why doesn't it all evaporate?
I think, well, a lot of the other compounds present have like a hydrophobic effect. So I'm guessing that if it was kind of trapped underneath
So it
these
dissolved
other
in
components,
it was
yeah,
like in solution, dissolved in
it kind of
solution.
can't evaporate just because the other ones are preventing water loss.
Did the mass spectrum, the fragmentation pattern, look like the fragmentation pattern of authentic toluene?
Yeah.
Yes.
And
Wow.
the like 92.1 is the molecular weight of
Yeah.
It's
so
exactly
Yeah, it was like the exact
it was really surprising to see it in an organic apple, but
Well, I have to congratulate both the Apple Wax teams. You guys really did some penetrating work here. I think that we've really advanced the state of knowledge in this area, certainly from a Chem 300 perspective. So thank you very much for that. And if there are no more further questions, it's time for us to get out of here. So please join me in thanking you. And let me please have your